All right, use number 3 for the Taylor polynomial error bound. This time we're going to work with the function e to the x, and our base point is at 0, and the x value that we're going to use is minus a half. And let's say that I don't know what order I want to use, but I do know the maximum error I want is 1 over 10 to the 4th. So an error of no more than 1 in 10,000. What order should I use for my Taylor polynomial so that my approximation has no more error than 1 in 10,000? This would be an important thing to know if you were, for example, designing a calculator. Scientific calculators, how do they spit out the values for e to the x that they do? Well, usually they use Taylor polynomials, but you have to know what order Taylor polynomial to use so that the approximation is accurate enough to be usable. So this is sort of almost a calculator design problem, I guess you could say. So if we want an error of no more than 1 in 10,000, what order should we use? Well, we're going to use the Taylor error bound, so we're going to have to find m. So let's do that at the beginning. Now, we don't know the order n, so when we find m, we're going to have our work cut out for us because we don't even know which derivative we're looking for here. Fortunately, for this particular function, e to the x, all of the derivatives are the same thing, e to the x. So when we put t in here, we always get e to the t. And remember, we need this inequality to be true for t values from a, the base point, to x. And a is 0, and x is minus a half. So where is e to the t biggest between 0 and minus a half? Well, it's biggest at 0 because that's 1, right? E to the minus a half is 1 over e to the half. E to the half is bigger than 1, so 1 over e to the half is less than 1. So e to the t is biggest between 0 and minus a half at 0. So that means we should choose 1 for m. So now e to the t is always less than or equal to 1 on this interval. Okay, so we have m. Now, we want the actual error. We know that the actual error in our Taylor polynomial is less than or equal to capital M over n plus 1 factorial times the absolute value of x minus a to the n plus 1. And we know what our maximum error should be. It should be 1 over 10 to the 4th. So if we insist that this error bound is 1 over 10 to the 4th, then we will have our actual error less than our desired error. So all we need to do is put everything we know into this inequality and then solve for the unknown, which is the order n. So let's put everything in here. We already calculated m. m is 1. The order n we don't know, so n plus 1 factorial. X we said was minus a half. A was 0. The order n we don't know, so n plus 1 less than or equal to 1 over 10 to the 4th. So our inequality that we're solving is 1 over n plus 1 factorial should be less than, times 1/2 to the n plus 1 should be less than or equal to 1 over 10 to the 4th. Okay, what a mess. So let's simplify this a little bit. 1 over n plus 1 factorial times 2 to the n plus 1. So I'm just putting this factor of 2 in the denominator in the same fraction as the factorial, less than or equal to 1 over 10 to the 4th. Now n only shows up in the denominator, so let's take reciprocals. N plus 1 factorial times 2 to the n plus 1. When you take reciprocals, that also turns around the inequality, so greater than or equal to 10 to the 4th. So now we need to solve this inequality. Well, we aren't going to be able to solve this inequality algebraically because, you know, we have a factorial here. There's just no way of sort of isolating the n when it's inside a factorial. So it seems like we're in deep trouble. But actually, remember, n has to be an integer. N has to be a positive integer. So we can start with n equals 1 and try it. Just see if it works. So when n is 1, we get, for the left-hand side here, 2 factorial times 2 squared. So 2 squared is 4, times 2 is 8. Is that greater than or equal to 10 to the 4th? No. So keep going. Next try n equals 2. Then you get 3 factorial times 2 to the 4th. So this is 6 times 16. Is that greater than or equal to 10 to the 4th? No. Still no. But we're getting closer. So what we're going to do is just keep plugging in larger and larger values for n until we find one that works. And the lowest value of n that we find tells us the order of the Taylor polynomial. So this is our third way to use the error bound for Taylor polynomials, using the error bound to find which order Taylor polynomial has the error we want. And there's one way to use the error bound left, and that is to worry about convergence of Taylor series.